Magnetic storms on the Sun are complex phenomena driven by the Sun's magnetic activity. These storms, also known as solar storms or solar flares, involve the release of a significant amount of energy in the form of electromagnetic radiation, including X-rays and ultraviolet light, as well as the ejection of charged particles into space. The science behind the formation of magnetic storms on the Sun is closely tied to the Sun's magnetic field dynamics and the behavior of charged particles in its outer layers. Key components and processes. Solar magnetic field. The Sun has a strong and dynamic magnetic field that arises from the convective motion of charged particles in its interior. This magnetic field is responsible for various solar activities, including sunspots, solar flares, and coronal mass ejections, CMEs. Sunspots. Sunspots are dark, cooler areas on the Sun's surface associated with strong magnetic fields. The number and distribution of sunspots change over an approximately 11-year solar cycle known as the solar activity cycle. Magnetic reconnection. Magnetic storms often result from a process called magnetic reconnection. This occurs when magnetic field lines from different regions of the Sun's surface come into contact, reconnect, and release stored magnetic energy. Solar flares. Solar flares are intense bursts of energy and radiation that occur near sunspots. They are associated with the sudden release of magnetic energy stored in the Sun's atmosphere. The energy release includes the acceleration of charged particles. Coronal mass ejections, CMEs. CMEs are massive expulsions of solar material and magnetic fields into space. These events often follow solar flares and are significant drivers of magnetic storms. CMEs can contain billions of tons of solar material, and when they interact with the Earth's magnetic field, they can trigger geomagnetic storms. Charged particle acceleration. During solar flares and CMEs, charged particles, including electrons and protons, are accelerated to high speeds. These charged particles can reach Earth and interact with the Earth's magnetosphere, leading to geomagnetic storms. Solar wind. The solar wind, a continuous stream of charged particles, mainly protons and electrons, emanating from the Sun, plays a role in driving geomagnetic storms. Variations in the solar wind, such as high-speed solar wind streams or coronal holes, can influence the Earth's magnetosphere. Impact on Earth's magnetosphere. When charged particles from the Sun, carried by the solar wind or CMEs, interact with the Earth's magnetosphere, they can cause disturbances. The magnetic field lines in the solar wind and the Earth's magnetic field may reconnect, leading to the transfer of energy and charged particles into the Earth's magnetosphere. Geomagnetic storms. The interaction between the solar wind and the Earth's magnetosphere can result in geomagnetic storms. These storms can cause fluctuations in the Earth's magnetic field, affecting communication systems, power grids, and satellite operations. Phases of geomagnetic storms. Storm initiation. The onset of a geomagnetic storm is often associated with the arrival of high-speed solar wind or the impact of a CME on the Earth's magnetosphere. Main phase. During the main phase, charged particles from the Sun interact with the Earth's magnetosphere, leading to magnetic field disturbances. This phase can last several hours. Recovery phase. The recovery phase marks the return to normal geomagnetic conditions as the Earth's magnetosphere readjusts. While these processes explain the general mechanisms behind the formation of magnetic storms on the Sun and their impact on Earth, predicting the exact timing and intensity of solar storms remains a complex challenge. Space weather monitoring and research continue to advance our understanding of solar activity and its potential effects on Earth's technology and infrastructure.